Good morning, everyone. Is it audible? Hello. If it is audible, please type in the chat. Okay, fine. So in the last class, we have seen the DTFT and its properties. Okay, and I have seen few problems in DTFT. So it's better to use properties while solving the problems instead of directly substituting in the DTFT equation, because uh, this properties helps a lot in dealing certain complex signals. Okay, instead of directly computing DTFT by substituting in the formula. Okay, so it saves time as well as uh, sometimes while implementing it also saves the computational complexities. Like if you want to uh, implement convolution between two signals, okay, and take the DTFTs, and in the frequency domain you just need to multiply. Okay, so all these things are handy. So, and we also seen the frequency response of the system, where for an LTI system in particular, this e power j omega n. Okay, so this e power j omega n will act as this e power j omega n will act as the eigen function of an LTI system. So that means when you pass this e power complex exponential signal through an LTI system, the output is just a scaled version of this complex exponential. The output we have seen that y of n is e power j omega n only, but this is the scaling factor which is independent of n now, and we call it as h of omega, or h of e power j omega, which is the DTFT of the impulse response of the LTI system. Okay. So this actually uh, is called the frequency. It is actually, in general, it is called the frequency response of the system. What is the frequency response of any LTI system? It is nothing but the DTFT of impulse response of the system, h of n or h of k. So this h of n is the impulse response of the system. If you take DTFT of this, so this we call it as frequency response of an LTI system, which is nothing but DTFT of impulse response, h of n. So this h of n, we call it as the impulse response of the LTA system. So what does it says actually? It is a function of omega again. Means in the frequency domain, this is a function of omega. The frequency response of the system gives us how the system is behaving at various frequencies. Okay, that we have since it is a complex quantity, that means it is not real, it is complex. H of e power j omega is a complex uh, frequency domain function. So it has magnitude and phase. So magnitude, this is frequency response of the system. Likewise, we have mod h of omega versus omega, we call it as a magnitude. This component, it has magnitude and phase. This is called magnitude response of the system, and the theta of omega, we call it as phase response of the system. So these things we have seen in the last class. And since if you take in the linear scale, small variations at lower magnitudes, okay, small variations cannot be observed in a linear scale. That's why we take the log to enhance that minute variations in the magnetic domain, in the magnitude response of the system. So for any, not only magnitude response, for any variable, if you have a smaller variations, if you just transform it to into logarithmic domain by just taking log of that value, so these minute variations will be enhanced at lower values. We get more resolution. Okay, that's the advantage of log. Okay, you know log x curve. Okay, it is basically, so all these lower values, okay, this set of lower values are mapped to large range. Okay, range of these lower values will increase, and the higher values range, it will decrease. Okay, it will compress the higher value. This is log x curve. It will compress the uh, log x. So it compresses the higher values. For higher values of x, the range, the mapping range is less, and for lower values of x, the mapping range is high. Okay, and further you can just scale this log x, okay, log 3x, 4x, something like that, to alter the slope of this curve at various points. Okay, that you can do. So and the base can be, okay, anything, but he has we will generally follow base 10, which will be easy to handle. So log base 10, and 20 is for example, if you take square here, then you will get 10 here. 2 into 10, or 2 into 10 log of this, or 2 will go into power here. So this is, we already seen, this is the power spectra. So 10 log uh, power spectra, sxx of omega. So this is 10 log is same as the 20 log of magnitude spectra. Okay, that you can just a manipulation. Okay, so if the gain is this g of g of omega, now we call gain function, because it will give the gain of the system at different frequencies. Okay, so if the g of omega is plotted like this, if for some system g of omega is like this, that means as we have already seen in the last class, at omega c. So 0 to omega c, the gain of the system is 1, and after omega c, the gain of the system is 0. Okay, that will give you the gain function. And actually, okay, this has to be 20 dB. So if you convert into, okay, this is mod h of omega, let us say. So this is mod h of omega. So if you convert into 20 log, this will become 0, and this actually not defined. So anyway, ideally we cannot take h of omega 0. This is the ideal case. So We'll see that. Okay. So 0 means unity gain. So g of omega value, if it is 0, that is the maximum gain we can have. This normalized gain we'll call, or unity gain. Unity gain means g of omega is 0 means h of omega is 1. Okay, mod h of, when mod h of omega is 1, so log 1 is 0. So this is g of omega is 0 means h of omega is 1. So that we call it as unity gain. Okay. And whatever the values less than 0, okay, g of omega is, if it is taking negative, that means it is not giving unity gain, it is giving some fractional gain. That means the input, no, the output will have lower gain. So we'll call it as attenuation or loss function. Okay, that means some gain is being discarded, so some loss is there in the output when compared to the input. And uh, and we call it as attenuation. That means at those frequencies the signal will get lower gains. Lower gains are negative gain in dB. Okay, so please understand these terms. Okay, attenuation, loss function is nothing but gain in dB is negative. If gain in dB is negative, we will call it as attenuation loss function. Why? Because our reference point is 0. Okay, so if g of omega, when you plot, so wherever you see 0, that means, okay, let us say this is the 0 axis. So and these are negative values here, -1, -2, and so on like this. So this zero gain region is said to be, means like maximum gain. We call it as pass band. Okay, and wherever the gain is less than 0, the signal is attenuated. That means for example, if you send x of n as 5 cos omega t, then 5 cos omega n. Okay, at this for when omega is in the range of 0 to some omega c here, then it will receive the maximum gain, that is 0 dB. And if your input sinusoid is greater than omega c, the signal will get attenuated. That means this 5 will become 4 or 3.7, something like that. Okay, so that is the meaning of gains, gain function. Okay, so the one 2 points to be noted is gain is 0 means that is the reference will follow. Okay, gain will be positive also in some cases, but generally we will say gain positive means it only occurs in the amplifier. Okay, so we don't talk about amplifiers in DSP, we just talk about filters. That means we need to pass some frequencies and we need to attenuate some frequencies. Okay, wherever the gain is 0 dB, that means that is our pass band. That means there the signal can be transmitted in that frequency range without any uh, loss. Okay, other than when the gain is negative, that means that the signal is transmitted through the system with some loss. That we call it as attenuation. Okay, so next we have seen some example of moving average system. So moving average system, magnitude and phase response of the system. So as m increases, your the low pass frequency capacity of the system, means a cutoff frequency decreases. Okay, so m is equal to 5 will act as will have high bandwidth than m is equal to 14. Okay, this is seen from the figure. As m increases, it won't allow higher frequencies compared to m equal to 5. So next we'll move on to this, yeah, response. This steady state response is is actually the steady state response. We actually, in general, we know that at a time t as t tends to infinity, whatever the response the system is giving, that is our steady state response. In general, we'll consider only steady state responses only. We don't take transient response into consideration in our signal processing. Okay. So because we are not assuming any circuitry, analog circuitry in our case, if you have any analog circuitry, then you need to consider this transients. Okay, how the network elements are behaving for when you apply immediately input like that. But in digital signal processing, everything is according to the real time. Okay, as soon as you give the input, okay, we need to first convert into digital form. And what computer do is just multiplication and addition. They can be operated with they can be executed within no time, and you won't get any transients in digital signal processing. Okay. So in general, everything whatever we do is in steady state only. Okay. So if you take an example, steady state output of a LTI system, let us say x of input is x of n. Okay. And this is real, completely real signal. You can always, from Euler's identity, you can just put this as x of n as some g of n into g star of n, so that the sum of a complex number and its conjugate is always real. Okay, that g of n happens to be this complex exponential omega naught n plus phi e power j omega naught n plus phi, and half will be there, so that if you take some, so this half a plus half a will become a. Okay. So what will be the output of the system? Output of the system is, okay, we have already known, we have already seen that this is a constant half a into uh, this half a into e power j omega j phi is a constant. It is independent of omega or n. So this is our input signal, which is a uh, what we call eigen function of the LTI system. So if you see here, so we have an LTI system whose input is e power j omega naught n. The output will be h of omega naught into e power j omega naught n. Since it is a this is because the system is LTI, and for every LTI system with real coefficients, we have this e power complex exponential as eigenfunction. Okay, this always happens. What is h of omega naught? This is the uh, frequency response of the system at omega is equal to omega naught, because we are giving some fixed omega naught here. So that is, so now if we multiplied it with half a into e power j phi, all are constants. Okay, into this e power j omega naught n, what will be the output? So since an LTI system, it satisfies this superposition, the homogeneity principle. So this is also half into e power j phi, this constant multiplied with what is e power j omega naught response. So this only h of omega naught e power j omega naught n. So now you, if you again, if okay, the same thing. So this I am calling it as some k. The same k multiplied by e power minus j omega naught n now. So here also the output will be that k into, okay, in the now in the place of omega naught we'll have minus omega naught into e power minus j omega naught n. Okay. So now when you add these two signals, okay, half a into e power j phi j omega naught n, half a into e power j phi e power j minus j omega naught n, that is nothing but a cos omega naught n plus phi. So this will be the these things will get added again. Okay. So now uh, this value h of omega naught and h of minus omega naught will be same for because this is a real LTI, real valued LTI function, LTI system. Okay, with real coefficients. The coefficients are nothing but h of n, means that means h of n is real here. For real LTI system, h of n will be always real. If h of n is real, from our complex conjugate property, okay, this h of minus omega naught is h star of omega naught. So h star of omega. So this will be same as uh, the magnitude will be same for these two, and phase will be complex conjugates. So you will get the same h of omega naught into a will be there cos omega naught n plus phi. Okay, here these two will be same for a real function. So yeah, so what I'm saying is h of n is real, h star of omega is equal to, or omega naught is equal to h of minus omega naught. Okay, that means their magnitude will be equal. So magnitude will be there, this one, and angle theta of omega. Okay, theta of omega will include inside this cos function. So in order to elaborate more, I'll just writing in another page. So we have two things. One is h of, this is half a into h of omega naught into cos omega naught n. Sorry, e power j omega naught n plus half into a into h of minus omega naught e power minus j omega naught n. So this is what we get from the superposition principle of LTI system. So this is the response due to half a e power j omega naught n, and this is the response due to half a into e power minus j omega naught. Okay, obviously this e power j phi will be there on both sides. Okay, so here also e power j phi will be there. So now what we are saying is h of n is real. That means h star of omega naught will be equal to, that is the symmetry property of dtft, h of minus omega naught. Okay, that means in the place of h of minus omega naught, you can put h star of omega naught. Then this will be half a into e power j phi. So in the place of h of omega naught, we'll put in magnitude and phase form, which is mod h of omega naught e power j angle h of omega naught. That we call it as theta of omega. Okay. So now on this side we have half the second term a into e power j phi, and mod h of omega naught will be because for h star of omega magnitude will be same and phase will be e power minus theta of omega will be there, minus j into. Why? Because this h star of omega will have same magnitude as that of h of omega, but the phase is since we have complex number, the only phase will have the negative sign. Okay, e power j phi j theta will become e power minus j theta. Okay, because for complex signal. I hope you understood that. And this multiplied by, okay, here you will have e power j omega naught n, and here you will have e power minus j omega naught n. So now when you combine these two, okay, so these two complex exponentials, you can write it as e power minus j into omega naught n plus, okay, theta of omega plus j minus j phi. Okay, here has to be, it has to be minus j phi. Okay, because since minus omega is there, so it is, has to be, yeah. So this will be plus j phi, and here it is e power j into omega naught n plus theta of omega plus j phi plus phi. Here j won't be there. So this is like e power plus j theta. This is e power minus j theta, and this is constant a into mod h of omega. A into mod h of omega half will be constant. So this is nothing but e power j theta plus e power minus j theta. So this is some constant k. Okay, k into e power j theta, e power minus j theta. So this will be cos theta. Okay, so this will be equal to some that constant into cos theta. Here is all these things after j in the brackets, omega naught n theta of omega plus phi. So omega naught n plus phi I'm writing first plus theta of omega. And what is this k? This k is nothing but 2 times half a into mod h of omega. This 2 half will get cancelled, and this k is now a into mod h of omega. here we have omega naught, so it is mod h of omega naught. So this is what we get when you give a cos omega naught n as input to the LTI system. This is the output you will get. This is an LTI system. So what is actually happening here? So for cosine signals, real signals, okay, you will get same cosine signal as output with the same frequency and phase, but phase will get an additional component theta of omega. What is theta omega? Theta omega here is angle h of omega. So that is what we have assumed here. Okay. So it will, this phase of this real signal will get modified by this corresponding theta of omega, and the amplitude of this real signal is modified by mod h of omega naught. So since if you do for cosine signal, this is the thing we need to see. Okay. So what is happening is this cos omega naught n, okay, the phase will get modified with theta of omega naught, and the amplitude will get modified with h of mod h of omega naught. Okay, so that is what we have seen till now. Okay, so what is the response of an LTI system for any real sinusoid is, okay, the sinusoids the frequency won't change, the sinusoids amplitude will change, and the phase of the sinusoid will also will be altered. How they are altered? They depend on h of j omega naught. Okay, whatever h of j omega naught you have, on that value it will change. So y of n has same sinusoidal waveform. The amplitude will get multiplied with mod h of j omega at omega is equal to omega naught. So for particular omega naught, and it has a phase lag relative to the input by theta of omega naught. Okay. So input is cos omega plus phi only, but output is cos omega plus phi plus some other theta of omega naught is getting added. That we call it as phase lag. With respect to input, what is the phase difference? This theta of omega naught. So the output will have this theta of omega naught. So this theta of omega naught in general should be positive, so that it experiences some delay. Okay, if it is okay, but that, okay, phase is phase can be anything depending on the frequency. So that is the steady state response for a real signal. Okay, so since for any signal can be represented as sum of uh, sinusoids, that we call it as Fourier series. Okay, that we'll see the Fourier series in discrete time domain, how it is defined. So for any common signal in general, okay, I'm telling beforehand itself, we just remember this point. Not only cosine or sinusoid, for any signal, okay, at some frequency, how the signal will get altered when when it is transmitted through a system is its magnitude will change as well as its phase also will change. Okay, so how the magnitude changes, it depends on what frequency response of the system, which is h of j omega. At that frequency, whatever magnitude the system is having, the same magnitude will be getting multiplied with the amplitude of the signal, and whatever the phase the system is having, the same phase will get added to the input. Okay, that is for any signal, not only sinusoid signal, that can be for any signal that we will see later. Okay, so now if you take causal exponential signal instead of e power j omega n, now we have taken e power j omega n into u of n. Okay, u of n is a causal signal, and it is 1 for n greater than or equal to 0. Okay, so when you substitute in this output, okay, this is uh, you can substitute in this convolution equation. Okay, and we can see that. Okay, so okay, I need to. So y of n is summation over k h of k x of n minus k is the convolution formula, and here our x of n is given as e power j omega n u of n. So that means it is defined only for n greater than or equal to 0, otherwise it is 0. Okay, so when you substitute this, so I'm writing k means the limits are default from minus infinity to infinity. Okay, h of k x of n minus k. So okay, in the place of x of n minus k, what we can write is e power j omega n minus k, wherever n is there replace it n, and u of n minus k. So what about this product? This product is non-zero whenever n minus k is greater than or equal to 0. Okay, so whenever n minus k is greater than or equal to 0, then only it is u of n minus k is 1. Otherwise u of n minus k, if it is negative, n minus k is negative, u of n minus k is 0, the whole thing will go to 0. So this summation is valid only for this limit. So what you can write is, now if assume that k is strictly positive, if you take k only positive, then you can replace these limits with k is equal to 0. Okay, and if k to n, okay, if k is greater than n, what happens? This n minus some value greater than n will be 0, negative. So then u of negative index is 0. So maximum limit is this one, h of k e power j omega into n minus k, and you can write u of n here. So that means we have uh, taken the whole thing multiplied with u of n. Okay, when n is greater than, this is for n greater than 0. This is only for n greater than 0 only. This will survive. If n is less than 0, u of minus something will be 0. So this is 0 multiplied by this thing is also 0. So this is what we get finally, the output. Okay, so y of n, this is what output we get, y of n. So now if you get a question that for n less than for k less, this is we consider only for k greater than or equal to 0. What happens if k is less than 0? The output won't be there for k less than 0, because when k is less than 0, okay, then n, if k is less than 0, n has to be negative. Yes or no? If k is less than 0, n minus k has to be greater than or equal to 0. This happens only when k is positive. Then n can take positive values. If k is less than 0, that means your impulse response is taking negative indices, that means it is not a it is not a causal LTA system. Okay, it is a non-causal LTA system, which is practically not possible. So that's why we have considered k greater than or equal to 0 for causal systems. In system is causal as well as the input is also causal. Input is causal because u of n is there. So for such cases, the output will also be always causal. So why you are saying output causal means the output has only indices n greater than or equal to 0 only. Okay, for n less than 0, u of n is 0, the output will be 0. So response of a causal exponential signal, okay, causal exponential sequence is also causal. So that is what our steady state response also, which is here we have this thing. Okay, and we use the frequency shifting, the time shifting property here, so that it will become this is equal to, you can write always h of omega into e power j omega n u of n, because h of k into, you can split this exponential into two terms, e power j omega n one term which is independent of this k can be taken outside, and this is e power minus j omega k, and h of k e power minus j omega k summation k is equal to 0 to n, we call it as h of omega, but it is not actual dtft of h of k, it is just you can call it as h cap of omega e power j omega n d omega. So that is the steady state response of a this one. So this one, there is some more analysis you can see here. This is not the actual DTFT, okay, actual DTFT of h of n, because if it is minus 0 to infinity, it is actual DTFT. It is 0 to n only. That means it is like partial DTFT, you can say. So if n is less than 0, this is always y of n is always 0 because u of n is there. If for n greater than or equal to 0, you can split this into uh, this two factors. Okay, 0 to infinity minus n plus 1 to infinity is 0 to n. That's what we are writing. This summation can be written as, this is 0 to n, so 0 to n, 0 to n range can will be written as, okay, I'm putting is to 0 is to n means 0 is to n means 0 to n range. Okay, it is always can be written as 0 to infinity minus n plus 1 to infinity. So 0 to infinity can be written 0 to n can be written as 0 to infinity minus n plus 1 to infinity. Okay, so in that way if you write, then this will be the this, okay, this will be the DTFT of this is the DTFT of the signal h of n, not this one, this, sorry, this one is h of j omega, because system is causal, so 0 to infinity, this one is this one, and this is first term is same as that we have actually we know this is the DTFT, and the second term uh, so the first term we call it as initially relaxed response, as this is the steady state response. This first term we call it as steady state response. In That means y of n is depending on e power j omega n plus 1, which is uh, okay, here k is n plus 1. So okay, this is not actually so practical, n plus 1 to infinity. So since still this is a causal signal only, but this value we need to compute, it is not so easy. So this is always we call it as a steady state response, okay, which is h of omega into e power j omega n. So for what we have started is, if the input is causal, what happens? If input is causal, for causal input signals, okay, the output is also causal. So output will also be assuming this LTI system is causal LTI system, the output is also causal. Since we have this is evident from this proof just we have seen. Okay, but for such signals we have uh, two terms. Okay, one is the steady state response of this system, which is generally h of omega into e power j omega n. Okay, which is uh, maybe which is this signal, this term, first term, and the another term is associated. This is k is equal to n plus 1 to infinity. Okay. This is very common thing. And this is called, the second one is called the transient response. Okay, n plus 1 to infinity, because every response is sum of steady state and the transient. So since we are not considering any initial conditions here, it is a steady state response exactly at n equal to 0. You can compute this. So this is the transient response, second term. Okay, so if you remove the transient response from the steady state response, then it is your actual response for causal signals. Okay, so what is the effect of this transient response? Okay, okay, with negative, okay, with negative sign, okay, it is called transient response. That means y of n is sum of y steady state of n plus y transient of n. So y steady state of n is this one, which is actual Fourier transform of the impulse response of the system into the input, and this is the transient response. Okay, minus, including minus. So for this transient, if you take the magnitude of this transient response for all n at various values of n, this is the magnitude, and we know this this term is less than 1. So by this Squarge inequality, this complex exponential magnitude anyway is 1, so you can replace with 1 and put a less than or equal to here. So this is h of k in, so the n plus 1 to infinity. So this is always less than this value. So k is n plus 1 to infinity value is always less than k is equal to 0 to infinity value sum. So this h of k, this is absolutely summable. That means this h of k is because we have taken assuming this is absolutely summable, so this value will also be absolutely summable. So transient response is always bounded. Okay, and as also as n tends to infinity, bounded signal means this is the condition. As n tends to infinity, this h of k value goes to 0. So these are all some implications of what is cause what is the effect of transient response for a causal signal. Because why transient response comes for a causal signal? Because suddenly until t minus 0 there is no signal. Suddenly you have applied a signal at t is equal to 0. Obviously you will get some transients, but those transients will die out as as n tends to infinity. As n tends to infinity, like a transient signal will go. Only steady state response will be there for any signal. Okay, for any system. So that's what it is shown in discrete time also. The transient response will go to 0 because y of n is bounded, because this is always a stable system. For a stable system, transient response will go to 0. Okay, that is one other point you note in the uh, uh, signals. Okay, so I will just we'll stop here this topic, and since we have other classes, so I will post the question in the group. Okay, the question link is given in the chat box. You just answer it. So someone in the chat box also respond, what if input is anti-causal? For a causal system, if you give the anti-causal signal as input, what will be the response? The response will be causal or anti-causal or non-causal. That is not as a part of this attendance question. Those who are interested, those who feel they know the answer, they can respond in the chat.